today we're going to talk about our model-driven design and development of an electromechanical actuation system, which has been a collaboration between our two companies. So let's start, and also thank you for the people who is watching us today.
Okay, hello everyone. We are going to start by explaining the project scope. With this partnership between CESA and Anzen, our main objective was to develop an electromechanical actuation system with model-based methodology, and particularly for CESA, the main interest was to evaluate the potential of model-based safety analysis using the ATICA add-on tool developed by Anzen. So in this case, CESA as a systems developer provider proposed the electromechanical actuation system with all of its systems requirements and the architecture of the model. And this was the electromechanical actuation system proposed is an already existing development, so this was proposed as a side project. And Anzen, as a RAMS developer systems provider, has proposed their ATICA add-on tool for Capella, and also helped with the model creation. This is the scope that we have been talking about. So first of all, I'm going to talk a bit about my company. This is Héroux Devtek. Héroux Devtek is the third largest landing gear manufacturer with facilities in Canada, in the USA, in UK, and the most recent here in Spain. They bought CESA in 2018, and we are here around 300 employees, which we develop and manufacture hydraulic systems, electromechanical actuation systems, and electronic systems. Here at CESA, we can provide a complete product lifecycle from architecture definition based on a technical specification to the complete development process, as including detailed design, stress analysis, safety and reliability analysis, or qualification testing. Once the equipment is qualified, it enters into the series production phase, where it is manufactured and assembled. And CESA also has the capability to provide in-service assistance. For example, we have the capability to provide maintenance, repair, and overhaul services. Additionally, we count with a research and development area that helps us acquire new capabilities. And we are involved, and we have developed many systems from different aircraft parts, for example, for the flight control systems, for the landing gear systems, the cargo hold area, or the hydraulic power systems for both military and also civil platforms. And we have clients from all around the world, from China to India, Germany, Brazil, from many different countries and backgrounds. So we are now going to talk a little bit about the case study here. So as we said, here the case study was an electromechanical actuation system for a primary flight control surface of a turboprop regional aircraft. The aircrafts have three control axes: the longitudinal axis, the vertical axis, and also the lateral axis, which are controlled by movable surfaces. In this case, we are centered in the aileron surface, which is located in the tip of the wings, and which is used to control the longitudinal axis. Here we can see the aileron located in the tip of the wings. In this case, what the customer wanted was a linear electromechanical actuation system, and they also demanded that the surface was moved by two actuation systems. Here we can see the aileron with the two actuation systems. And the actuation systems is based on an electromechanical actuator, the EMA, and on the electronic control unit, the ECU. And two working modes were specified by the customer: an active mode, in which the system was responsible for the aileron movement, and also a backdrive mode, in which the system was not in control of the movement. This is because in case that we detected a failure in one of the systems, it could be switched to the backdrive mode, and the other system would be able to control the aileron movement. So taking a deeper look into the electromechanical actuation system, first of all, an actuation system receives the energy and the command signal and transforms it into a motion, into a force. So in this case, particularly, it converts the electrical energy and the command signal into a linear mechanical force. Here we can see the diagram of our system. So in this case, the electronic control unit receives the electrical power supply from the aircraft control system, and it also receives a speed command. And in return, it has to provide the EMA position and also some sensing parameters. In this case, the EMA is a direct drive linear EMA in which it consists of an electrical motor and a ball screw, which transforms the rotary movement of the electric motor into a linear force. Additionally, it has an electromechanical normally closed brake, which has to be able to stop the actuator movement in case of an uncontrolled movement or just simply to maintain a fixed position. This brake is commanded directly by the aircraft control system. So the ECU only transmits the signal but does not have the capability to activate or to decide whether to activate or not the brake command. And well, additionally, it has the position sensor, which is a dual LVDT sensor in order to feed back the position to the aircraft control system, because the customer wanted to be the one responsible of closing this position loop. As we said at the beginning in the scope, one of the main interests was to evaluate the model-based safety analysis, the possibility to include a safety analysis within the model-based approach. So I'm going to explain briefly the safety aspects of this project. So this system had to be developed within the ARP 4761 framework and the ARP 4754A, which is normally the mandatory environment within the aeronautical industry. In this case, as it is applied for a primary flight control system, which is a safety critical system, the level of rigor of the development had to be the most stringent, which this means a development assurance level A according to the ARP 4754A. In this project, also catastrophic and hazardous events were defined, which are the most severe failure conditions that have been defined. In this case, a catastrophic event was the inability to stop a runaway. A runaway means an uncontrolled movement of the surface. By defining it as catastrophic, this meant that no single failure shall lead to this catastrophic event. So we had to have a combination of two events in order to avoid the single failure point. In this case, the combination was of the inability to detect the runaway or the uncontrolled movement and the inability to break the surface, to stop the surface movements. Here in the table, you can see the system quantitative safety requirements defined by the customer, which had to be flowed down into the contribution of the ECU and the EMA. Now here we can see the physical aspect of the electromechanical actuator and its distribution. So apart from the features already mentioned, the electrical motor, the ball screw, the position sensors, it contains also a resolver in order to have the angular position of the motor to be able to close the speed control loop, and it also contains some two temperature sensors in order to be able to detect the actuator's temperature and monitor it itself. In the table, you can see some of the main performance aspects of this electromechanical actuator. So now here we can see an overview of the electronic control unit. In this case, a control monitor architecture was decided to be implemented in order to be able to comply with the safety requirements. Having two channels increases the possibility of detecting any anomaly or failure. So in case of detecting any of these, we could switch to a safer mode. Here in this box, you can see the main boards that were included in the control unit. For example, the power subsystem, which was in charge of managing the 270 DC supply for the electrical motor or the 28 DC supply for the brake. We have also the brake subsystem, which is in charge of transmitting the command signal received from the aircraft controller in order to activate or deactivate the electromagnetic brake. We also have the motor drive subsystem, which is responsible of powering and controlling the electrical motor, or the FPGA subsystem, which is in charge of developing the control signals and also of the communication between the control and the monitor channels. And just as I said before, the position loop is not closed in the control unit. It is closed outside by the aircraft. The ECU only closes the speed control loop. And now Luis is going to talk about a trade-off of the MBSA tools that was performed.
Thank you, Elena. I'm going to present now the task where Anzen has been involved in this project. But first of all, let me present our company. We are Anzen. Anzen stands for safety in Japanese. We started in Madrid in 2019 as a company specialized on providing support services on system safety and reliability engineering. 4 years after today, we have spread our footprint into the United States, the Arab Emirates, and also Switzerland. We are European leaders on these two disciplines, safety and reliability, but now we want to expand into the model-based safety analysis by developing our internal framework called ATICA that we are going to present today. So going back to the project, our model-based approach started with a deep evaluation of the market tools. We analyzed Capella System Composer from MATLAB and Cameo System Modeler. As you may know, different tools means different advantages, so it is very important to define, first of all, which tool covers the company necessities in a better way. So most of them shares the same methodology because all the information of the system is breakdown into the operational, functional, logical, and physical architectures. But as we said, it is important to define, first of all, the features that we want to analyze. We started with the evaluation of these features that I'm showing to you in this table. Some of the tools, System Composer or Cameo, seems to be very powerful because of the simulation capability. However, we focus our point more in the collaborative work, the open source customization, and also the cost of the license. In addition to the user experience related with the methodology, in this case for Capella, the Arcadia one, the deal with architectures, the sequence diagrams, and also the functional change, in addition with the requirements management. So after the evaluation of these features, we said that Capella covers our necessity the best. So we choose Capella as our base model-based system engineering tool. And after deciding to choose Capella, we build a whole digital engineering framework around Capella. So everything starts with the requirements, as you may know. Compliance with requirements is completely essential for the development of a product. In our case, we treat our requirements in DOORS. So we are creating an interoperability between DOORS and Capella in order to have a unique source of authorized requirements. In addition, we enrich our Capella model with the simulation parameters of Simulink, which is our base simulation tool. And finally, I want to present to you our in-progress digital tool, which is called ATICA. ATICA was born to consolidate a safety framework by connecting the models with a powerful backend in order to compute, analyze, and automate the safety analysis that are performed in the industry. We call it framework because rather than being just constrained to Capella, the idea is to have a very transversal tool which could benefit all the disciplines along the system engineering process. Pointing to this case, we have developed for Capella ATICA model-based safety analysis, which connects with the model using the plugin ATICA for Capella, which is ready to download in our website. So I really invite you to try it and maybe leave some feedback. But for the whole performances of ATICA, I encourage you to see the webinar that Pablo Lopez gave the last month, where everything and these topics are addressed. So next, let me explain to you how we understand the system engineering process. Here we have requirements management, model-based safety engineering, and model-based safety analysis. So everything starts with the idea of a need. For example, people need airplanes to travel fast. That's what we call the stakeholder needs. And they are represented in the operational analysis in order to shape what need the operation need to accomplish. Our proposal here is to develop this analysis always in parallel with the certification basis and the safety point of view. So in this case, we mentioned the certification basis of EASA for the aerospace industry. You may know the EASA CS23 or 25, but this will vary depending on the project. Now, with the operational analysis performed, we could establish the functional requirements that will guide you to form the very preliminary system architecture where all the functions of your system will be addressed. So if we analyze this function and the possible dangers or losses of this function, we could develop the functional hazard analysis. If we break down the systems into subsystems, we arrive until the logical architecture, which should meet the system requirements. And in parallel with the logical architecture, we develop, following in this case, the aerospace recommended practice 4761, the failure tree analysis, and also the FMEA and the FMEC. So keeping adding details to our architecture, we arrive until the physical architecture. And if the system is complex enough to have a behavior in order to be simulated, to design and simulation also. So at this point, we arrive until the final design of our product or our system. So the whole reliability prediction figure of the system could be performed. In this case, following FIDES standards, or even the military handbook, or failure rate databases as the NPRD. So if we encapsulate all of these tasks into tools, we get that the requirements management are going to be performed in DOORS, as we said, the model-based system engineering, of course, in Capella, the simulation in MATLAB, and finally, the model-based safety analysis with our tool ATICA. Focusing now on just the requirement management, what we are creating is an interoperability between DOORS and Capella. So there is a unique way or a unique source of authorized requirements in the way that if any engineer updates something in DOORS or in Capella, we bring those changes to the other platform. So we have a bidirectional operability, which is the purpose of this interchange. Right now, we are dealing inside Capella with the requirements viewpoint in order to manage the requirements, also with Python for Capella to import and export this data. And the idea on future is to replace Python for Capella by a graphical user interface in order to import and export the data in a very comfortable way. Maybe just to clicking in a button and then the interchange is performed. So taking a closer look of the DOORS platform, we have here our requirements classified into the requirements itself, the headers, and also some information. So this is the way that we are going to treat them. Every column is going to be transformed into an attribute inside Capella and inside our requirement object. And then the headers, as you see from the left, are going to be transferred into folders. So in this way, the designer could access inside Capella this information in a very comfortable way. So we maintain a logical order and we maintain all the requirements inside its own folders. These folders are initially gave from the client, so the structure inside Capella is quite logical and also comfortable. Now, with a closer look into Capella, we get that the more important requirements are going to show and are going to be displayed on the diagrams. This is, of course, not possible to do for all the requirements because they wouldn't fit in the window. So the other one are going to be completely allocated and linked to the components and functions that implements the current requirement. And then in order to manage the data together and also to see the attributes and edit them, we use the mass visualization, which is quite similar to Excel and also very comfortable to use. So right now, with all the requirements method defined, we could show to you how we build our system model for the aileron system.
Okay, yes, so now we are going to see an overview of the model that we have created. So we are aware of the many functionalities and the many diagram options that Capella can offer in order to unravel the complexity of the system. But here we have tried to keep the model as simple as possible while maintaining all of the necessary information. So here in the first operational level, we show what the customer expects. In this case, the customers needed an electromechanical actuation system that provided certain functions while complying with a development assurance level A. The functions were to be able to provide the actuator movement, a control movement, provide status parameters in order to be able to do health monitoring, and also to be able to stop the movement and maintain its position. In this case, we defined also the modes and state to specify when the functions are carried out. So continuing with the system analysis, in this case, we want to break down the operational capabilities that we have defined in the upper level. So in this case, we have performed a breakdown of the functions, and we have also created the functional chains in order to show the interrelationships between the different functions. So here, this is the model at system level we have created. We created 3 different functional changes, and here we can see a more detail of the functional change named feature sensing, which, for example, we can see that it has sensed features of the aileron control, the brake, or its movement, in order to be fed back to the aircraft control system. At this level, we have included also the system failure conditions, which we have performed this using ATICA, which later on Luis will expand on how ATICA can allow to perform this. And in this case, we also here have started linking all of the requirements into the functions. The requirements, as Luis explained before, were imported from DOORS into the operational level for a simpler view, to be able to simply view all of the requirements together, but they can be referenced from all of the different levels of Capella. So by using the features already explained by Luis, we can link the requirements to each of the functions in order to see which requirements affect which functions. So now, moving onto the logical architecture, here our main goal is to show how the system is going to accomplish its functions. So here we have included the main components of the system, the electronic control unit and the EMA, and we have also increased the decomposition of the functions and the functional chains that were defined at the system level. So we can allocate the functions into the main components, and we can also increase the detail of the functional chain. In this case of the feature sensing, we can see, for example, that it also captures information from the power management bus, for example, and then it's also fed back to the aircraft controller. Here we have also introduced the main failure modes of the functions with ATICA, and we have continued linking the requirements to all of the different functions. And lastly, here at the physical level, we want to show the real implementation of our system. So we show the physical components of the EMA, and we also show the control boards that make up the electronic control unit. For example, here we can see a detailed aspect of the ECU control board. In this case, we can see how all of the different blocks are interrelated amongst them, and how the information that they share and their interfaces. Additionally, in this physical level, when we introduce all of the physical components, we want to also include all of the necessary information in order that the different specialists in the team can perform the detailed analysis. So in this case, for example, for the three-phase permanent magnet synchronous motor, we have included information such as the number of poles or the dynamic friction. So in this way, the specialists know that the needed information is included in the system, in this model, and so they can be able to perform all of their analysis, because here the idea is that all of the team members can contribute at this level to our physical model. At this level, we have also included all of the lower level failure modes, and we can associate them to the effects at higher level. So we can relate the failure mode defined in the physical level to the ones defined in the logical level and in the system level. So this way we have them all connected, and this increases the awareness of the rest of the team of all of the safety aspects that they are usually not aware in the traditional way of systems development, in which the specialist had kept their information and was not in a unique source. And of course, at this level, we also link the requirements to show which components are affected by which requirements, and the specialist can know what they have to comply with. So now Luis is going to explain a little more about how ATICA for Capella can be used.
Okay, thank you, Elena. Now I'm going to explain how ATICA for Capella works. If you are familiar with the Arcadia methodology, you will know that every system has the system functions. So what we have created here is the object failure condition in order to define the effects and the severity of losing these functions. This failure condition help us to define the functional hazard analysis from the safety point of view. So following exactly the methodology Arcadia, as every system function could be broken down into logical functions, they will have its own failure representation, which in this case is called the functional failure. Performing these steps again, we arrive until the physical layer, where the behavior components and physical function will have the failure modes with the failure effect, quantitative, and will be traced with the logical, with the functional failures and also with the failure conditions. In this way, this is the fully traceability of the object programming. So this helps us to perform a a top-down analysis, like the faulty analysis with the traceability between all the failures, but also the failure mode effects and criticality analysis and the summary of them, which is the FMES, in a bottom-up approach. So starting in the system level, the way that we create a failure condition is to drag and drop the functionality from the Capella palette. So we drag and drop into a function, and then a failure condition will be created in our system model tree. Taking a closer look of the object itself, we see that it is fully integrated with Capella, and it is important to remark here the way that we trace downstreams the information of the failures. So with this group of failure condition, we could create the functional hazard analysis. This is a structured table where all the conditions are listed in their own functions. And also we show the fields that the aerospace recommended practice, so 4761 says for the development, which are the description, the modes, the failure type, the effect, and also the severity. So as you see, this generation of the functional hazard analysis is completely aligned with the respective regulations. This help us a lot to define the possible dangers of losing every function and to enrich the safety point of view. It could happen that some failure condition could have a direct impact on our design. So for example, if we create one which is catastrophic, this will imply that no single point of failure could drive that condition. And also it establishes a safety quantitative requirement. So a new functionality that is right now under consolidation is some kind of assistance during the modeling process where, for example, we could sum all the failure rates of the low-level failure modes and raise a warning if they are if they sum a probability bigger than the quantitative requirement. Also, we could, for example, check the architecture and see if the no single point of failure is met. So we could raise a warning when all the derived requirements are not met. So going back to the system and the architectures, we arrive until the logical one, where the functional failures behave quite similar. And it's important here to remark that we could trace upstreams with the condition and downstreams with the failure modes. So finally, the last level, which is the physical one, has the failure mode with its own failure rate. And this is the way that we trace all the information. If we represent this into a tree diagram, we get the whole traceability of the failures model in our system, which help us a lot to define this failure net and to define the high-level effects of the low-level failure modes. With this failure net, we also generate the FMES, and I will show you how. The Arcadia methodology is a top-down approach. By breaking down every failure condition, we develop the failure net of the whole system. And once the system is completely designed, we start the verification using analysis like the FMECA and the FMES. So our value proposal here is to use the FMES to directly generate the failure mode effects and summary, and to set this common point from the top-down and bottom-up analysis in the way that every failure condition defined in the high-level system will have a related failure mode that drives that condition, so no condition is empty, but also that every defined failure mode in the FMECA has an already defined failure condition in the high level. So this is the active verification of the top-down approach by means of the bottom-up study. Our idea here is to extract this failure net from ATICA and import them in our reliability tool, which is Isograph. So the generation of the FMES related with the FMECA is fully assisted. The next step that we want to show you is the connection with Simulink.
Yeah, Luis and
Yes?
Elena, just to let you know, you have just a couple of minutes left for the presentation.
Okay, perfect. Thank you, Stefan. So the last step here to show is the connection with Simulink in the way that we are treating the information. Every component is going to be shown in different points of view. For example, the architecture itself, where the electronics and mechanical engineers could upload the parameters of these physical devices. But the same component will have several representations. For example, the one with the simulation view, where all of these parameters will be the same because the component is the same. But here we show only the components that should be simulated in other platform. So we connect this with, this is just Capella, and we connect this with Simulink by means of interchange information, this simulation information between Capella and Simulink. So the same way, if something is updated in Simulink, we receive those changes and we update the model in Capella and vice versa. So finally, let's define the next steps and end with the conclusion of this collaboration.
Okay, so after developing this project, the main conclusions that we would like to point out is that we've seen that with that MBSE has a great utility for complex and highly integrated systems because we have all of the information available and organized in one source. Also, we can say that MBSA through ATICA enriches the model and increases the awareness of the safety aspects to the rest of the team, because traditionally in the early developments, safety was sometimes thought of a specialty as a side specialty, but nowadays it has been proven that it is very important to take into the consideration the safety aspects from the very beginning of our design. And this is a way that everybody in our team can be aware of these aspects. We can also conclude that it has helped the cooperation and the coordination between all of the different team members, because all of the important information is included in the model. We know which information has to be included in order that the different specialists, the stress specialist or the mechanical designer, can be able to perform their analysis with the information included in the model. But it is also too important to evaluate the learning curve of using model-based system engineering, because obviously it is not the same if we implement this for a simple or a unique alone equipment, or if we want to implement this for complex systems. Here at CESA, we develop systems, but we also develop simple equipment, which are only, for example, one part. So in these cases, maybe the learning curve does not pay off, because the management of the project is simpler. But it is true that when we are taking into account a larger, bigger, and complex system, like, for example, a landing gear system, which has many different subsystems, like the extension and retraction system, the braking system, or the steering system, it is beneficial to use MBSE, because it allows to maintain the information in one unique source, and it is easier for the rest of the team to understand the functions and the flow of information.
Okay, so just the last words to end the presentation. We want to remark that every project sets new goals. So from Héroux Devtek point of view, we will implement the model-based system engineering, including the safety analysis, as a new system development methodology. And from the point of Anzen, we will enrich the collaboration with CESA, and we will expand the development of ATICA in order to cover the show analysis, like the hidden failure analysis, the analysis of redundancies, the cut sets, which is almost ready to be done, and the failure tree. So thank you for your attention, and now if you want to perform some questions, we will be pleased to answer it.
Thank you very much.
Yes, thank you, Luis and Elena, for this excellent presentation. Max, this one. How does Capella differ from, for instance, a reliability workbench by Isograph? Is one considered superior to the other?
Okay, I think that maybe the aspect here is not considered anything superior to anything, because different tools have different scopes. For example, Capella, the scope of Capella, what we're using for is to develop these architectures and maybe enrich another platforms. So, for example, we could use Capella to enrich Isograph in the way that we export what we call the failure net, or equivalent the FMES. So we are not going for now to use Capella to perform the reliability like Isograph. So I think that it's important just to consider the different fields to cover for the different tools.
Yes, and I think that here in Capella, we maybe don't need to get to so much detailing of the physical components or of the detailed design. No? For example, when we develop a control board, here in Capella, maybe we don't introduce all of the information of all of the resistors or capacitors or diodes that are included in the control boards, for example. But we do include that sort of information in the reliability workbench as Isograph in order to perform the reliability predictions or so on. So maybe introducing so much detail into Capella maybe not in mind of what we have right now.
Mm-hmm. Okay, thank you, Kevin.
Okay, next question. How much time did it take to develop the model?
Okay, so this is a complicated question because sometimes it's not as easy as it seems to make a quantitative evaluation of the hours. But I'll say that depending of the knowledge of their team and the people obviously who's going to model this time. But I think that there is not so much hours here implied, but in comparison with the hours that this could save from other activities. So from our point of view, I don't know if we could say the exact hours, but
well, yes. In this case, it is important to point out that this electromechanical actuation system that we have implemented in Capella and with MBSE is an already existing project. So it wouldn't be really the real scenario for considering how much time it took for developing this system, because we could say we already knew what the outcome would be. So if we had to start from the beginning with for example having the technical specification from a customer, it would take more time to develop the model. So the time that we have taken right now wouldn't be a realistic value to consider. So this is something that we have performed in order to see the feasibility of implementing model-based methodology, but it has not been the real way we have developed this system.
Thank you. How do you connect Capella to Simulink? Is the communication between the two bidirectional?
Okay, so right now this is not a direct simulation inside Capella. So what we are doing is to export the data and the parameters of each component. So when you simulate in Simulink, you can import just data from Capella, for example, the number of poles of the motors, the inductance, and rest of parameters. So the communication mean is some kind of interchange file, for example, Excel or a template, where you could import and export, of course, bidirectional, in order to communicate both of them. And we just import and export this data between the both platforms.
Thank you. Does ATICA support user-defined enumeration for risk assessments? For example, scoring enumeration for ISO 26262 or IEC 61508.
Okay, so right now we are just focusing the aeronautic industry, as we said before. But the idea is very important to have a very transversal tool, and if the community needs them, and if we could develop it, our idea is to support this kind of enumeration and standards to be fully transversal to other industries, for example, automotive or naval, etc., and also the aerospace environment. So yeah, of course, it's an idea that we want to implement.
Okay, maybe a more specific question. Is the model development for EMA generic or it's control surface specific? And if generic, how did you model in Capella the different loads at different surfaces? Did you confront the sizing problem? And maybe second question, looks the safety requirements like 1E8 for DLA. How will the Capella model reflect to comply with this requirement?
Okay, so in this case, the model developed for the EMA was based on the specification that we received from our customers. So in this case, we received a specification for the complete system, for the EMA and the control unit, for a control surface, which in this case was the aileron surface, but actually it is based on an actuation system. And we used that as a basis in order to develop the model. These requirements that were set by our customer were already specific for controlling the aileron surface. And the way in which we modeled it in Capella, we first wanted to include all of the functions of our system in a higher level. For example, the function of controlling the aileron surface, the other function that meant that we had to be able to stop the actuator's movement, and the third function, which was to include a way in which to detect the health of our actuator and provide this back as feedback to the aircraft control computer. So, and then when we developed all of these functions and subfunctions in the operational level, in the system level, and in the logical level, when we went to implement this on the physical level, in which we gave more detail about the physical components of the EMA, for example, we included the electrical motor as a physical component, the ball screw, the brake, or for example, the physical sensors. In those physical components, we included the information needed for the different specialists to be able, to perform their analysis. So, for example, and we also linked them to the requirements. So, in the specification, we had requirements regarding the loads that it had to withstand. So we linked those requirements to the blocks of the EMA. So the stress specialists, for example, could do the sizing of the components and could see if the EMA, if the physical components of the EMA, for example, the attachments, the physical attachments to the surface and to the aircraft will be able to withstand those loads. So we only included like the important information that would be useful for the specialists, but other calculations and other analyses were performed outside Capella. And regarding the safety requirement, what we did was, well, in this case, for example, the DALE requirement, the 1 to the -8, for example, that system failure condition was included in the system level, and it was related to the functions that performed, that were involved in that failure condition. For example, if we refer, for example, to the jamming functionality, the probability of the actuator being jammed, we know, for example, that the ball screw intervenes in that failure conditions, or the brake, for example. So we have included, linked that requirement to the different components that are involved in that failure condition. So that's the way we reflect that way. And in the physical component, we introduce the failure modes and we link them to those failure conditions defined in the higher levels, also with their failure probabilities.
So you could just add the probabilities of the failure modes and check if that are lower than your safety requirement.
Yes.
So again, Elena and Luis, thank you very much for this very insightful presentations.
Okay, bye. Thank you,
Okay,
Stefan.
thank you.